And there we go. Okay. So welcome everybody to the webinar of today. The speaker of today is Stefan Alberti, and he's gonna talk about Lagrangian dispersion in a quasi-two-dimensional models of ocean submesoscale turbulence. So as usual, I quickly introduce the speaker, and then I leave him the floor. So Stefan Alberti is assistant professor at University of Lille and researcher at UML laboratory in Lille, France. He received his PhD in 2006 from University of Torino in Italy and University of Nice, France, and worked as a postdoc in 2007 at the University of Helsinki in Finland. From 2008 to 2010 at the University of Grenoble in France, and from 2011 to 2012 at the École Normale Supérieure de Paris in France. His research interests focus on transport properties in turbulent flows, reaction transport systems, complex fluids from a theoretical and numerical point of view. It's with great pleasure that I introduce Stefano Berti, and Stefano, I leave you the screen share. I stop sharing my screen.
Okay. So can you see my screen?
Yes, we see your screen. Okay. And now it's full screen mode.
Oops, sorry.
That's good.
Okay, so good afternoon, everyone, and thank you, Francesco, for this introduction and for the invitation. So I would like to start this talk discussing briefly some general features of the ocean general circulation across scales. So let's consider first this red arrow below, which marks some important ranges of length scales for the ocean. On the left, we have large planetary scales, while on the right, we have the microscale. So on very large scales, the ocean circulation is forced by climatic processes, and due to the Earth rotation is essentially two-dimensional. This is a state which is called balanced because the flow is close to an equilibrium, the geostrophic equilibrium between Coriolis and pressure forces. However, this equilibrium is unstable and gives rise to many different processes, and I won't enter into the details of these many different processes. I just want to remark here that the more one goes to smaller scales, the more the flow departs from a balanced state, it becomes more three-dimensional, and it is no longer dominated by the Earth rotation. So in this talk, I don't know how to, okay. So in this talk, I will be interested in this range of scales in this blue circle, which is called meso and submeso scales. So these ranges of scales are characterized by somehow turbulent dynamics that are close to two-dimensional flow. So this turbulent character is a common feature of these two ranges of scales. However, they also have important differences. And I would like to comment a little bit about this. So first of all, if we look at the typical sizes on the horizontal, mesoscales are much larger, namely from few tens to few hundreds of kilometers, while submesoscales are considerably smaller, namely of the order of 1 to 10 kilometers. Mesoscales penetrate much deeper below the surface, and they evolve on longer time scales, namely from few weeks to months, while submesoscales are much faster, evolving on time scales of the order of a day. More importantly, vertical velocities in these two range of scales are very different. At mesoscales, they are very small, so the flow is really close to being two-dimensional, while at submesoscales, they can be up to an order of magnitude larger. And this is important not only from the point of view of physical oceanography, but also for the coupling of the ocean with the atmosphere and for marine ecology, that is for plankton dynamics. Currently open question concerns the dynamics of these submesoscales. We know today from high-resolution general circulation models that submesoscales should be characterized by a large spatiotemporal variability. They should be strongly energetic, and once again, they should provide an important contribution to vertical transport. So spatiotemporal variability is illustrated by these two figures above, which are satellite images of the chlorophyll concentration in two different regions and in two different seasons. So in two different months, to be more precise. So this means that we expect that submesoscales behave differently in different geographic locations and in different moments of the year. An important point to remark here is that today we still have no access to the flow field itself from satellite data because satellites only resolve the mesoscale. So all the indications we have are either from numerical simulations or from indirect observations. For this reason, I think that Lagrangian studies in this context are particularly interesting. First of all, today Lagrangian drifters provide a geographical coverage which is almost global, and they have good temporal resolution. In the last years, this type of studies with Lagrangian drifters have put in evidence enhanced relative dispersion, which should point to energetic small scales in different regions of the world ocean. So this is illustrated by this plot on the bottom right, and in particular by these black points. So what is shown here is the dispersion rate as a function of scale, measured in the Gulf of Mexico from surface drifters. So these black points that scale approximately as r, the distance to the power minus 2/3, highlight that dispersion rates are much higher than we previously hypothesized, which in a sense corresponds to these white points. So here there is a question, which is what type of flow dynamics may be responsible of this type of behavior. So this is the outline of what I will try to tell you about. At the beginning, I will introduce the type of models that I use to study the upper ocean turbulence, which follow into the class of the quasi-geostrophic approximation. Then I will present you some results from a study concerning Lagrangian pair dispersion in this type of flows, which, as I will show, can be cast in a common framework, which is called generalized to the turbulence. Then I will try to extend the picture to a somehow more realistic model, still at the level of the quasi-geostrophic approximation, but this time including mixed layer instabilities. Finally, if I still have some time, I will try to say a few words about what we are doing today, which concerns geostrophic corrections. So before going to the proper subject of this first part of the talk, I would like to show you here what we know about submesoscales from an Eulerian point of view today. So as I already said, these indications come from numerical simulations, and here I show you some vorticity fields from a high-resolution numerical simulation performed in Grenoble. So what you see in these left panels is the North Atlantic, and clearly you can recognize this meandering jet, which is the Gulf Stream. However, beyond this strong current, you can see plenty of different structures of different sizes. Nevertheless, there is an apparent difference between the top and the bottom panel, which correspond to two different seasons, winter above and summer below. So if we zoom on a certain area like this black square, we can have a better feeling of how the flow looks like. In winter, it is more energetic at small scales and characterized by a broad population of eddies of different sizes. Instead, in summer, as you can see here below, it is much less energetic at small scales and somehow it appears smoother in physical space. So while what I'm going to show concerns idealized models, while these are realistic models, I think this conveys well the different structure of the flow field at submesoscales with which we would like to compare. So in this study, what we wanted to do was to explore the connection between Lagrangian and Eulerian statistics, which is typically non-trivial, and it often relies on dimensional arguments. This is related to the motivation. As a kind of motivation, you can consider the drifter studies I showed before. And we wanted to do so in idealized models of 2D turbulence that are relevant for the upper ocean, and in particular with more or less energetic small scales. So the main questions I will try to address are the following ones, namely, how does the dispersion of Lagrangian tracers behave in time and as a function of the pair separation distance? How is it related to the characteristics of the turbulent flow? And possibly see if there is a link between the Eulerian and Lagrangian concepts of locality. So this is a short reminder about particle pair dispersion. So in this context, one works with a large number, capital N, of Lagrangian tracers that evolve according to this equation, where U is the velocity field. Relative dispersion is defined as, in this expression, it is the average over all particle pairs of the squared distance between two particles in a pair with a given initial separation. The asymptotic behaviors of this quantity are well known. At small times, one expects a ballistic t-squared scaling for relative dispersion, while at large times, relative dispersion should scale diffusively, namely linearly in time, due to essentially uncorrelated particle velocities. At intermediate time and length scales, one possibility to obtain the behavior of relative dispersion is to consider relative diffusivity, which is proportional to its time derivative. And by doing so, you see that the relative velocity appears, which can be dimensionally related to the kinetic energy spectrum. So for a spectrum which has a power law behavior of exponent beta, one has two different predictions depending on the value of the exponent. If beta is smaller than 3, meaning that small scales are sufficiently energetic, relative dispersion should scale as a power law with an exponent depending on this parameter beta. And this is the regime that is often referred to as local, because in this case, the dispersion process should be controlled by flow features that have the same size of the separation distance y. When beta is larger than 3 instead, and the flow is not sufficiently energetic, it's much less energetic at small scales, relative dispersion should grow exponentially in time, and this regime is called non-local because it should be controlled essentially by the largest flow features. So what we wanted to do was to test this type of predictions in turbulent flows that are idealized but still relevant for ocean dynamics. So for this purpose, we chose to work in a dynamical approximation, which is called quasi-geostrophy. And here I try to give the main ingredients of this type of dynamics. So this holds for a rapidly rotating and highly stratified fluid in the Boostinsk approximation. In particular, the Northby number is clearly should be very small. So the dynamics can be expressed at lowest order in the Rossby number by these two equations. The first one is vorticity equation, where omega is vorticity, u is the incompressible geostrophic flow, and f is Coriolis parameter, and w is vertical velocity. The second equation is the buoyancy equation, where n is the buoyancy frequency. And finally, there is a third relation which links the buoyancy to the stream function, which is just a combination of geostrophic and hydrostatic balance. So from these two equations, one can eliminate vertical motion. And this is interesting because it gives a single equation, which is this one, which states the conservation of an important quantity called Q, which is potential vorticity along the geostrophic flow. So potential vorticity is defined like this. There is this part, which is usual relative vorticity, plus this vortex stretching term. This system must be complemented by a boundary condition at the surface, and in the hypothesis of a rigid lead, this condition is the conservation of surface buoyancy along the surface flow. So this is a quasi-geostrophy, and now I would like to introduce another system which is also considered as a paradigm of surface ocean turbulence, which is surface quasi-geostrophy. So in the upper part of this slide, I just recall the main dynamical equations of QG dynamics, and I want to stress here that in this case, the flow is driven by potential vorticity in the interior. Notice also that in the case of a strictly two-dimensional flow, the stream function becomes independent of the depth Z, and then one recovers the usual vorticity conservation. So SQG is similar, but there is an important difference, which is that one assumes that Q, the potential vorticity, is strictly zero in the interior, and therefore the flow is driven by buoyancy at the surface. So skipping some details, here in this green rectangle, you have the non-dimensional formulation of the SQG model. And here I just want to remark that this is the dynamical equation that one considers, that is the conservation of surface temperature by the surface flow. So a nice feature of these two systems is that they can be cast in a common framework, which is called generalized to the turbulence. So to do this, one considers a conserved active tracer Q, which evolves according to this equation, where U is the geostrophic flow. The coupling between the tracer and the stream function is expressed in Fourier space by this relation, where you see there is an exponent alpha, and due to this exponent alpha, this model encompasses a whole class of different models. Each model is specified by a different value of this parameter alpha. Not all of these models are physically relevant. However, two of them are, in particular, for alpha equals 2, one has the quasi-geostrophic model. For alpha equals 1, one has the SQG model. In the first case, Q is relative vorticity, and typically one expects a kinetic energy spectrum like this, a rather steep spectrum, while in the other case, Q represents surface temperature, and the kinetic energy spectrum is much more energetic at small scales. Also, from the point of view of spectral dynamics, these two systems behave differently. The QG dynamics are marginally non-local, while the SQG ones are characterized by local interactions. So what we wanted to do was to study tracer dispersion, Lagrangian tracer dispersion in these two types of models. And now I would like to come to some results concerning this study, starting from the properties of the turbulent flow. So in this upper row here, I show some snapshots at a given time of the tracer Q for different models characterized by different alpha. Here on the left, you have the SQG model. Here on the right, you have the QG model. These are simulations in free decay that we performed in this study. Below, you have the corresponding kinetic energy spectra for different values of alpha. So what we can see here is that in the SQG case, eddies are present from the largest to the smallest scales, and the kinetic energy spectrum is close to k to the minus 5 which is the theoretical expectation. In the QG case, instead, the flow is characterized by more thin and quasi-passive filaments, and its kinetic energy spectrum is much steeper, namely steeper than k to the minus 3. It is this blue line here. So let's now go to the results concerning relative dispersion, and here I will start discussing the time-dependent statistics. So here we considered up to 2 million particle pairs with the given initial separation y0, and then we varied this parameter. The first thing I would like to remark is that independently of the type of model, at short times, in all cases, we have a rather clear evidence of the expected ballistic behavior. However, at intermediate times, dispersion appears to grow less rapidly than predicted. So in the SQG case, it grows less rapidly than this T-cube Richardson scaling, which is the expectation. And by no means in the QG case, this blue curve, we are close to an exponential behavior. So the situation improves a bit when one reduces the initial separation as expected, and in particular this is so for the SQG case where we somehow recover the expected behavior. Nevertheless, in the QG case, it is still difficult to observe exponential growth. So to try and clarify this point, we resorted to fixed scale indicators, because indeed relative dispersion by definition has a drawback, which is due to the fact that averages are performed at a fixed time, and instead dispersion regimes should change in correspondence to different length scales. So this means that at a given time, one may have different pairs at different separations that are counted together into the statistics. So it is generally advised to consider also statistics at fixed length scale. And for this, we mainly consider the finite size Lyapunov exponent, which is defined here. From a physical point of view, this is a dispersion rate at different scales, and it is defined as up here. In this expression, the average is over all particle pairs. Tau is the time needed to observe the growth of separation from a scale delta to a larger scale R delta, with R a prescribed amplification factor. So if one has a power law spectrum of exponent beta, then dimensionally you can see that the FSLE should also scale as a power law with an exponent depending on beta. More precisely, the expectation for the SQG case are delta to the minus 2/3, and in the QG case, the FSLE should be constant. So through this indicator, we get results that are closer to the theoretical expectation, as it can be seen in this plot. Indeed, in the QG case, the scaling is close to the delta to the minus 2/3 scaling, while in the QG case, this blue curve, the FSLE is almost constant, and this gives a first indication of non-local dispersion in this model. To further substantiate this point, we also considered higher order statistics, and here I just would like to discuss this lower plot. Here I showed the pair separation PDF for the QG model at different times. So you see that when the variables are appropriately rescaled, all these PDFs collapse rather nicely onto a single curve, which is consistent with the Lundgren PDF, whose expression is given here, which is the theoretical expectation for a flow like this that is not very energetic at small scales. So in our view, this provides strong support for non-local dispersion for this QG model. So this is a summary on this part. So we have shown that relative dispersion essentially agrees with the theoretical expectations, which can be better appreciated using fixed scale indicators. While the concepts of locality are very different from an Eulerian and the Lagrangian point of view, if you want, there is a sort of correspondence between the two. And perhaps more importantly, if we have to say what type of flow is more appropriate to explain the enhanced relative dispersion that is observed from real drifters, I would say that this study suggests that SQG could be relevant for this. Nevertheless, the SQG dynamics are highly idealized, so clearly this is not all of the story. And this is one of the reasons why we next considered a slightly different model, which includes an important feature, which are mixed layer instabilities. So before presenting this new model, I would like here to add this new feature, which is absent in the SQG. So here above, I just recall some features that I already introduced. What I would like to point out is that turbulent dynamics at the surface of the ocean should strongly depend on the seasonal cycle, because this modulates the depth of the mixed layer. And this is not present in the SQG dynamics. So different mechanisms have been proposed for the generation of submesoscale. On one side, one can have mesoscale-driven processes like SQG, which is surface trapped and lacks a mixed layer. On the other, more recently, there have been mixed layer instabilities that have been proposed, which are interesting because they have a seasonality due to the presence of the mixed layer, and they give rise to somehow more three-dimensional motions. It is also interesting that these different mechanisms imply different vertical structures of the resulting flows. So in this sense, I think that studies dealing with Lagrangian dispersion at depth can be a useful tool to understand the coupling between the surface and interior dynamics, which is notoriously difficult to access because it is difficult to perform measurements below the surface at depth. So this is a schematic view of the model we then considered, which is still quasi-geostrophic, but it is made of two layers. This provides a simple description of the thermocline and the mixed layer dynamics. So the layer on top has a lower stratification, and it is aimed to represent the mixed layer, while the layer below is aimed to represent the more stratified thermocline. In both layers, one assumes a constant potential vorticity. And clearly, as you have two layers, you can also identify this system through these three discrete levels. And here, this intermediate level corresponds to the mixed layer depth when the mixed layer is present. Here, I just would like to remark that this mixed layer depth typically in the ocean is of the order of 100 meters. From my point of view, a nice feature of this model is that one can consider the dynamics in the presence of either of the two layers separately or in the presence of both, so that different dynamics can be tested and compared. So what we did was to study the turbulent dynamics of this model using realistic parameter values for the mid-latitude ocean, and we looked at the dynamics of tracers down to depths corresponding to minus 500 meters, that is well below the mixed layer. So in equations, this is how the model looks like. Here I will skip many technical details, but if you are interested, you can find them in this nice paper by Callis and co-authors. So the dynamics is specified by the evolution of potential vorticity on these three discrete levels that I just pointed out. And potential vorticity is at each level is proportional to buoyancy. So in a certain sense, you can think of these dynamics as SQG-like dynamics on three discrete levels that are then coupled. The coupling can be conveniently expressed in Fourier space in a matrix form. Here I don't put the expressions just because they're a bit lengthy, but you can find them also in this paper. The system is forced by these two terms. The first one is corresponds to a mean zonal flow. That is, if you want, a flow in the x direction, which is a vertical, which is a mean shear in the vertical. This other term corresponds to mean meridional potential vorticity gradients, that is in the perpendicular direction. So these are the necessary conditions to have instabilities, baroclinic instability in both layers. That is a submesoscale instability in the mixed layer and the mesoscale instability in the thermocline. Yes. So, jumping to the results, this is this slides is meant to show how the turbulent flow looks like in the three different models I consider, that is the thermocline only case, the mixed layer only model, and the full model in which the two layers are present. Going from top to bottom here corresponds to going to depth. And what I show is vorticity normalized by its RMS in a certain subregion. So if we look at the surface flow in the absence of the mixed layer, we see that it is characterized by different structures of different sizes, from large to smaller ones, and a rather filamentary and many filaments. However, as soon as we go to depth, small scales decay, and already at minus 100 meters, essentially all small scales have disappeared. They reappear again close to the bottom due to energetic SQG-like dynamics on the bottom level. The situation is quite different in the presence of a mixed layer, because indeed you see that throughout the whole mixed layer, that is down to minus 100 meters, essentially from a statistical point of view, the flow is unaltered. It keeps its small scale structures. However, when we go below the mixed layer, small scales decay, as in the previous case. In the full model, the phenomenology is the same. However, close to the bottom, we recover part of the small scales due to SQG-like dynamics, as in the first model. A little bit more quantitatively, these are kinetic energy spectra for the three models. In the top row, I show them at some selected depths. Below, you have a more complete picture versus depth. I also would like to remark that while in this model, at least from a numerical point of view, one only needs to integrate the dynamics on these three discrete levels, the string function characterizing the horizontal flow can be obtained at any depth. So these dashed lines are reference depths at which we perform Lagrangian advection experiments. So if we look at spectra, what we see is that in all cases, the spectrum at the surface, that is the red curves, is energetic at small scales. However, in the absence of the mixed layer, it rapidly changes. It becomes much steeper, namely steeper than k to the minus 3. In the presence of the mixed layer, this only occurs below the mixed layer. You see that at minus 100 meters, corresponding to this blue curve, the spectrum is very similar to the one at the surface, and instead, below the mixed layer, it becomes steep. This green line here corresponds to the spectrum at the bottom in the full model, which is again energetic to SQG-like dynamics at the bottom. The same occurs in this thermocline-only model. So going to Lagrangian statistics, what we did is very similar to what was done in the previous study. To point out a difference, here I would like to remark that the advecting velocity is the full velocity, meaning the one obtained by turbulent fluctuations and the mean flow, and drifters evolve at a fixed depth. So in this sense, we neglect vertical velocity, which is justified by the fact that vertical velocity only appears at next order in the Rossby number at this level within this approximation. So we considered in this study original pairs with a rather small separation corresponding to half a kilometer, which is also half the grid spacing. So the first thing we did was to repeat the exercise we did in the previous study, that is to try and identify different dispersion regimes, this time as a function of depth in the different models, and try to relate them to the characteristics of the turbulent flow. I won't spend too much time on this, but I still would like to point out that essentially we find that dispersion is local at the surface in all cases, corresponding to the red points. and it rapidly turns to non-local, corresponding to this flat FSLE in the absence of a mixed layer, while this only occurs below the mixed layer in the presence of it. This is for the FSLE for horizontal dispersion at a given depth, but the same picture is confirmed by other indicators. So instead of insisting on this, I would like to spend more time to discuss another thing that we did in this study, which is slightly different. So the aim was to try and explore the correlation of Lagrangian dispersion at different depths. And for doing this, we resorted to a generalization of the FSLE, which is called FSLE of the second kind. So the general framework in which this tool was introduced is the one of trajectories evolving in different flow realizations, but starting from the same initial condition. This is different from the usual FSLE, because in that case, one has two trajectories in the same flow, but starting from a different initial condition. So this tool was introduced some time ago and often used in relation to modeling, that is to quantify uncertainties or unresolved components in the governing equations. So this is illustrated by this cartoon. One model corresponds to this plane, where one has this red trajectory. The other model corresponds to this lower plane and the blue trajectory. Both of them start from the same initial condition, and one can still compute a distance between the two, and therefore compute an FSLE. So what can we expect dimensionally for this indicator? Let me first discuss a very special case. Let's imagine to have two velocity fields that only differ by the small scale energetic content. So one flow has a given kinetic energy spectrum, the other flow has the same kinetic energy spectrum at large scale, and no energy content at scales smaller than at wave numbers larger than a cutoff wave number. So the early growth of trajectory separation, that is for separation smaller than the cutoff length scale, can be dimensionally estimated, and this is what one gets, a ballistic behavior, where V star is the typical velocity difference. So this can be rephrased dimensionally in terms of a scale-by-scale dispersion rate, that is an FSLE, and this ballistic behavior would correspond to a delta -1 scaling in the limit of small separations, while at larger scales, at larger separations, the FSLE of the second type should recover the behavior of the usual FSLE of the first type, because in this case, if you want, trajectories can no longer realize that they evolve in different flows, because at large scales, these flows are statistically equivalent. So what we wanted to do was to adapt this methodology to our problem to investigate trajectories evolving at different depth, starting from the same horizontal position. This is because in our case, the more you go to depth, the less small scales you have. So in a certain sense, the situation is similar. So we generally put a particle at the surface and one at a depth which varies below, at a depth below the surface, and then we varied this depth. So due to the different small scale energetic content, the expectation for this indicator, which here I call lambda V, just to remark that is intended to quantify these interdepth dispersion properties, is the following. At sufficiently small separations, it should scale as delta to the -1, while at larger separations, it should recover the behavior of the FSLE of the first type. However, our model is characterized also by vertical shear, which can play an important role. Indeed, one can estimate dimensionally what the FSLE of the second type should look like. And for a mean shear rate, one has this expression, scaling in delta to the -1, and more generally for a velocity difference, for whatever velocity difference, one should have this other prediction always scaling as delta to the -1. So these are the results that we obtained in our three different models. Let me start discussing first small depths and in particular this thermocline only case. So at small depths, the FSLE of the second type is close to the FSLE1, namely close to the delta to the -2/3. This is true in this range of large separations in the absence of a mixed layer, and on a broader range of separations in the presence of the mixed layer. So the crosses here correspond to one tracer at the surface at one at -50 meters. So what we see in this thermocline only case is that while what I just said is true at sufficiently large separations, the FSLE2 deviates from this behavior at smaller separations, and it approaches a delta to the -1 scaling. This is due to the lack of small scales that occurs going to depth. Notice also that the typical length scale of the submesoscale instability is around 10 kilometers. So it is reasonable that at small depths, this deviation is related to this lack of small scales. The more we go to depth, the more this scaling approaches delta to the -1, and the more the vertical shear is felt. And in the end, this dominates the behavior of this indicator. In the other two models, the situation is for some aspects similar and for some other different. First of all, if we look at small depths, what we see is that the FSLE2 is close to the FSLE1, that is the delta to the -2/3 scaling, essentially over all this broad range of separations. This is due to the fact that throughout the whole mixed layer, the flow hasn't lost small scales. When we go to larger depths instead, the FSLE deviates from this behavior and somehow approaches the delta -1 behavior due to both the lack of small scales and the importance of the vertical shear. So these slides essentially gives the same message, but perhaps I hope in a better way. Here, what I show is the FSLE2 compensated by the different predictions. In the main plots, the compensation is by the total shear prediction. In the insets is with delta -2/3, that is the behavior of the FSLE1. So what we see is that in the thermocline only case, the total shear prediction works well, at different depths. However, some deviations can be noticed at separations larger than 10 kilometers and for sufficiently small depths. If we compensate with the other prediction, we see that this is the range of scales and depths where the FSLE2 was close to delta to the -2/3. The vertical shear prediction works, I would say, only order of magnitude in the presence of the mixed layer, that is in these two other cases. And in particular, important deviations are observed at small depths, where by compensating by the other prediction, we see that indeed that was the correct scaling. So I think that the message of this study is that there is a decorrelation at depth, which is very fast in the absence of a mixed layer, but it is to large extent controlled by the vertical shear. So perhaps it can be parameterized with not too many difficulties. On the other hand, in the presence of a mixed layer, the dispersion properties at the surface are a good proxy of those in the whole mixed layer. So this is my conclusion on this part. I let you read it. It's just it's only what I just said. Instead, I would like to say that these two studies were performed in the framework of the preparation of a new satellite mission, which is called SWOT, which should bring currents at the surface of the ocean, which with much larger spatial resolution. So I think that in particular, this study is interesting because it shows that if we improve the resolution at the surface, we can use this type of new information also to learn something about deeper flows. And if I can take 5 more minutes, I would like to show you what we are doing, what we are starting to do now, which concerns hagiostrophic correction. So we try to go beyond quasi-geostrophy. So the motivation is even more related to next generation altimetry data, and in particular to this SWOT satellite, which is expected to be launched in fall this year. Here you have the countdown to launch taken from the web page of the satellite. And clearly this is a very sophisticated instrument, so I won't enter into all the technical details, which I also do not know too well. But instead, I would like again to stress that this satellite should allow to explore surface currents from mesoscales down to scales of the order of 10 kilometers. So this is one order of magnitude improvement in spatial resolution. So I think that here there is a big opportunity to observe energy cascades at finer scales. So it will be a big novelty. However, there are also some caveats, some drawbacks. In particular, surface horizontal flow will be obtained from sea surface height, SSH, via geostrophic balance. And we know that geostrophic balance holds at sufficiently large scales. The more we go to small scales, the more the flow departs from this equilibrium, is no longer in a balanced state. So the important question, one of the important questions from my point of view is what is the impact of small scale, that is hagiostrophic processes, on this type of data? So more precisely, the main question we are trying to address is the following. Can we assess the extent to which SWOT SSH is a good proxy for surface horizontal velocity, and this as a function of spatial scale? So before showing you what we are trying to do, let me give you a little bit the feeling of what hagiostrophic motions do. To do this, I will consider again a study with drifters, real Lagrangian drifters in the Gulf of Mexico from Dasaro and collaborators, which corresponds to these images. Here time grows from left to right, and look at the magenta points, which are positions of drifters. At the beginning, they occupy an area which has a typical size of 10 kilometers, but as time goes on, they gather together in a very narrow region of the order of 60 meters. So this is better illustrated by this movie taken from this study, where you see what happens. Indeed, drifters get closer and closer together until they seem to disappear in a single point, which is this very narrow region. So this tells us that hagiostrophic motions provide an effective compressibility on the surface horizontal flow, which clearly is associated to important vertical velocities. So this type of motions are also important, for instance, for marine ecology. So what we want to do is to compare Lagrangian dispersion statistics in models, in idealized models, that can have or not hagiostrophic corrections. And in particular, we will rely on the FSLE of the second kind. The theoretical framework we have taken is one which is called SQG+1. It was introduced by Hakim and collaborators in this paper. The derivation of the model is a bit long. However, the main idea is not very difficult to understand. One has SQG dynamics, that is conservation of surface temperature by the surface flow, and this coupling between surface temperature and the stream function in Fourier space, but this time the velocity, the advecting velocity u is computed at next order in the Rossby number. So a nice feature of this model is that it allows to reproduce something which is present in reality, but not in the SQG case. For instance, the cyclone-anticyclone asymmetry, which is summarized in this vorticity PDF. That is this difference between this right tail of the PDF and this left tail. These are at Rossby equals to 0, 1. So, as I said, we want to compare relative dispersion indicators in the presence SQG plus 1 and Rossby larger than 0, or in the absence SQG and Rossby equals 0 argiostrophic corrections. In particular, we want to explore the intermodal dispersion characteristics by adapting the same methodology of the FSLE of the second kind. So in this case, one trajectory will evolve in the full SQG plus 1 model, the other one in the SQG model, that is, it will be advected only by the geostrophic component of the flow. And we expect that this type of study will allow us to estimate a typical length scale above which the two trajectories behave in a similar way, and therefore the velocity provided by the satellite is accurate enough, at least for these Lagrangian dispersion applications. Another point we would like to address is clearly clustering events due to the non-zero flow divergence. This may be interesting in relation to marine ecology problems, but also for the transport of whatever tracer at the surface of the ocean, as for instance, plastics. With this, I conclude and I thank you.
Thank you, Stefano, for your presentation. Very interesting, and thanks also for the last part about perspectives and generalization of your study. I would suggest to open the stage for questions then. So all the participants who would like to ask a question, just feel free to unmute your mic. Yeah, Johan, go ahead.
Yeah, so hello, Stefano. I had a handful of questions that came to me during the presentation. Maybe some of them you've already partially answered. One question I first asked myself was about why you were looking at Lagrangian trajectories. And I was wondering whether it was to compare with the study of people who are living like small tracers and small buoys, following their path, and then try to infer the properties of the, let's say, Euler flow.
Mm-hmm. Yes, this is the main reason. The fact is that today the majority of indications we have from experimental studies in this range of submesoscales, which we can loosely say small scales at the surface of the ocean, come from Lagrangian drifters, that is, buoys drifting at the surface of the ocean. So from the properties, from the statistical properties of dispersion, one tries to infer the characteristics of the turbulent flow, as you said. So the idea was to try and see what type of simple dynamics could give rise to Lagrangian statistics comparable with those observed in the real ocean.
Okay, so another question I had, maybe it's probably a short answer, is that so at some point you when you had this two-layer model, several-layer model, you talk about vertical shear. And so in the ocean basins, you also have these, well, you have all these motion at the surface, but you also have, like, in meridional overturning circulations. And I wonder whether this vertical shear was included to reproduce this kind of motion.
Not really. We are on much smaller scales. We consider a domain size on the horizontal, which is 500 kilometers by 500 kilometers, and a depth down to 500 meters. The overturning circulation goes to the abyssal ocean. I think the average depth of the ocean is around 5,000 meters. So you may think this as a portion, for instance, of the Gulf Stream. So you have a mean flow which varies with depth because the action of the wind, of the steering actions at the surface lose intensity when you go to depth, but we only look at the surface ocean.
Okay. And another question I had later in the talk, so you were talking about ageostrophic motion, and at least from the study of the atmosphere, I kind of put the ageostrophic motion into kind of boxes. That's often I view it's either like convection, maybe turbulent or laminar, and inertial gravity waves, at least in the atmosphere. And I don't know what was the physical process that could cause this ageostrophic motion near the ocean surface.
I'm not an expert on this. I'm not a true oceanographer. However, the processes you mentioned are among those that are important also in the ocean, in particular tides, internal tides. You can have Langmuir circulation, which is kind of a more small scale turbulence in the first layers of the ocean due to the steering by the wind. These are some examples. In this study, we are not really interested in reproducing a specific phenomenon, but just to include some corrections to quasi-geostrophic equilibrium in a perturbative way that is going at next order in the Rossby number. However, this work we are now discussing with some oceanographers in Brest who carry out general simulations with high resolution general circulation models. And we would like to adapt this study also to trajectories obtained in that framework. And in that case, ageostrophic motions will be essentially those induced by internal tides.
I think that was about what I could think. So thank you for your presentation and the answer to my questions.
Thanks.
Okay. So
I have a quick question for Stefano. Perhaps slightly nerdy. I'm sorry, Stefano, if it's nerdy. In the first, can you hear me?
Yes. Hi, Christos.
Okay. Hi. In the first part of your talk, you mentioned you mentioned at some point the PDF of pair separation distance.
Yes.
I thought you mentioned it also only for the case which you called alpha equals 2, which was a very steep spectrum.
Yes. We computed it also in the other cases.
So there are predictions for the other cases, by the way. Did you try to check?
Yes. When you have alpha equals 1, that is the SQG model, and the spectrum is Kolmogorov-like, we do get Richardson PDF at least in a certain range of times. Here I was showing only this because it was to provide support of something which was not clear from relative dispersion. So in the other case, more or less, all other indicators were pointing to the correct behavior.
Okay.
In this case,
but even between alpha 1 and alpha 2, there are predictions for this PDF. And I don't know if you check them. You can actually predict the PDF between alpha 1 and alpha 2.
Yes. You mean for intermediate values of alpha?
Yes, that's right. Between 1 and 2, that's right. You can again predict the PDF.
I think this is in our paper. It's a kind of generalization of Richardson PDF.
Yeah, in some sense it is. Yes. Yeah. So you obtain the right PDF also for the other cases.
Yes.
Okay.
Yes.
Right. Then you mentioned a strong dependence on initial conditions, initial separation. Was that for strong dependence on initial separation of the pairs?
What is the value?
No, it was dependence on initial separation of the pairs, correct?
Yes.
Okay, I mean, to what extent is that actually contrary to the usual Richardson way of thinking?
I think I didn't get the question.
To what extent could that be actually contrary to the usual Richardson way of thinking? This very strong initial separation dependence.
No, I don't think it is in contrast. What I wanted to highlight is that if you look at relative dispersion, that is statistics at fixed time, it is more difficult to get the expected behavior, but in the end you get them. Particularly for local dynamics. I mean, here, when the initial separation is small enough, you do get something close to Richardson.
I assume the reason for this dependence is that the flow is not time dependent enough and particle pairs can be captured in structures for a long time.
There is this, and there is also that you need, if you want, a sufficiently extended inertial range. I mean, particles should lose memory of their initial condition before entering the inertial range and spend some time there. Sorry? But
they don't necessarily always do so. They can actually sometimes keep memory for longer than that. Is that correct?
But I don't know about special cases. Here, I forgot to say the time is normalized by the time over which they lose memory of the initial condition. So somehow you enter a self-similar regime.
Okay, thank you, Stefano.
Thanks.
So we can see if there is someone else who would like to ask a question. So once again, just feel free to unmute your mic, or you can write in the chat and I can report the question. Then maybe I can ask you actually one question in the previous slide, like in one of the previous slides in which you were showing the velocity, the profiles at different depths. You were showing the flow at different depths starting from the surface. Yes, that's it. Yeah, the vortices. So as far as I understand from this slide, basically the full model, like the two simplified models, can help you to interpret the full model, because the mixed layer model tells you that there is a strong coherence between the surface and 100 meters, and the thermocline model, the thermocline contribution only basically tells you that there is a certain how to call it, a certain increase of mixing and less filament structure at the bottom, which you find also for the full model. So is this kind of correct? Like splitting the interpretation into the first part, it's well predicted by the mixed layer. The second part is well interpreted by the thermocline.
In a sense, yes. In a sense, yes. This is one of the nice features of this model. That is that you can choose the type of dynamics you want to explore and compare them to see which one would be more meaningful. The other is that I think all of these situations could happen in the ocean. For instance, a thermocline only model means a model in which essentially there is no mixed layer, and the mixed layer depth varies with season. So in summer, typically it is very, very shallow. So you are in a situation closer to this, while in winter, due to strong winds and storms, it gets deeper. So you come closer to one of these situations. And also the depth of the thermocline varies. Mm-hmm. So in the context of this study, we did not, we were closer to what you were saying, that is trying to add or remove a dynamical ingredient to understand the dynamics of the model, and in particular of the full one. But in principle, either situation can occur in the ocean.
And another question just related once again to this slide. Can this picture provide you with somehow an estimate, at least in a scaling argument, about the vertical velocity? Because no. In this model, vertical velocity is neglected. So yes,
you have dynamics on these everywhere, in particular at this level, and this level.
Mm-hmm.
These are the dynamics where you need to specify the levels where you need to specify the dynamics. And then from the dynamics on each of these three levels, you can get the stream function at each depth. But all these flows are strictly two-dimensional. This is due to the quasi-geostrophic approximation. I think it's possible to diagnostically, as geophysicists say, get the vertical velocity. That is, from the horizontal flow, there is a way to compute the vertical velocity, which is, by the way, the same that is used in the atmosphere. It's called omega equation. It's an equation that it's a combination of the others from which you can get the vertical velocity a posteriori, if you want. And this is at next order in Rossby. So here we chose to neglect it because it should be small, but I think it should be possible to compute it, and indeed I think it would be interesting because in that case, for instance, this type of model, in my opinion, would be very interesting in relation to plankton dynamics if one has vertical velocities.
Yeah, well, actually, probably this is close to what I was thinking. I was thinking actually to if it has been done to develop like an asymptotic theory in which basically you scale the vertical velocity differently than how you scale the in-plane velocity, such that you kind of get an epsilon parameter in front of all your W's,
yes.
kind of thing, and then the leading order is what you compute, and the higher order is basically has the leading order inside the convective term, and all the rest is higher order expansion.
Yes, according to the way I understand quasi-geostrophy, this is the thing.
Okay.
This is the thing. However, I think here, I mean, to me, it's not evident how to apply this reasoning here, taking into account these different levels, that is, these boundaries in this layered model. I would know in a semi-infinite domain, but here, I think, as I said, it can be done, but I still haven't tried. Okay. But the approach, I think, it's very close to what you were suggesting. Okay. I don't know if I answered the question.
Yeah. That was very clear, basically.
Yes. By the way, I noticed that Joran correctly says that with the omega equation, you can get the QG vertical velocity.
Yeah.
And the divergence. So.
Yeah. And then say, but can you still have problems with the AG vertical velocity? For instance, the horizontal divergence you discuss at the end is AG and not diagnosed by omega equations.
I don't know about that. I think it should be possible, but it's not evident in this moment to me how to do that.
Then let's see if there is someone else who would like to ask a question. So once again, just feel free to unmute your mic and ask the question, or you can write in the chat and I will report it. Okay. So this doesn't seem to be the case. I just have one last question for you on the last part. You presented when you showed the video of the drifters, and yes, and here you mentioned about the compressible flow, because basically it's compressible on the surface, right?
Yes, exactly.
That's okay. And are there like reliable techniques from a handful of drifters like these ones to reconstruct somehow the 2D divergence of the flow?
Yes.
Because then and then the idea is that you can compare this with the vertical velocity you could eventually predict with the omega, right?
Yes, it is exactly like that. The only problem with real data is that you need at least 3 particles. You need a cluster, because what you need to measure is the rate of deformation of areas of polygons. And from these, you can get both divergence and vorticity. So in recent years, there have been an explosion, I think, of studies like this. The technique was developed in the 70s, I think. Mm-hmm. But the problem was that until recent years was that there were not enough data. So the statistics were fluctuating a lot. And also that the other thing is that it is only recently that the design of drifters have been adapted to investigate such small scales. Mm-hmm. But yes, the way to do it essentially is to consider a triangle, to have the fewest number of particles, and to measure how its area varies in time. From this, you can get the divergence. It's rather easy to show it.
Sure. You get,
then there are other indicators of clustering that are used, but for divergence, this is the usual one.
And I assume that there are like higher order corrections for like for the time in this kind of estimate, because the divergence field is not going to be constant in time, and when you compare the same triangle after a short time, you are moving in a your divergence is moving as well, right?
Yes.
Your divergence. Mm-hmm.
Yes, in a certain sense, it's based on a Taylor expansion, the method. Yeah. So this also gives rise to large errors with real data.
Yeah, sure.
But indeed, in simulations, this is one of the things we are planning to do.
Yeah. In simulations, you can refine the time scale as much as you wish, such that that contribution kind of counts less than the
But still, it's not trivial to
no.
good results over a long time.
Yeah, true.
As I tried, I can tell you that at least for me, it's not very easy. But then this is for the divergence, which certainly is interesting. But there are also other, luckily, there are also other estimators of clustering. So
sure.
It is possible, I think, to study clustering in this type of flows.
Okay. So thank you once again. Let me see, just to run over last call. Is there someone else who would like to ask questions? Just feel free to unmute your mic or write in the discussion. I can report a question. Okay, that doesn't seem to be the case. Then thank you once again, Stefano, for this very interesting talk and for replying to so many questions. And thank you everyone for participating in this webinar. And I invite you to thank our speaker again and wish you a good evening and hope to see you soon next Thursday.
Thanks, Francesco, for the invitation again, and thanks everybody. Bye.
Bye.
Bye-bye.